An ingenious structural system, the truss is used in roofing, bridges, towers, and various other applications to span large distances with maximum material efficiency. Widely utilized today in architecture, civil, and mechanical engineering, its origins trace back further than one might expect. But how far can we go in uncovering its history? This talk will proceed backward in time, searching for the earliest evidence of trusses, as well as the structural concepts at the foundation of their conception. We begin with a definition. In engineering, a truss is a structural framework composed of straight members connected at their ends to form a rigid system. These members are typically arranged in triangular units, leveraging the inherent rigidity of the triangular form. Truss members primarily experience axial forces, either tension or compression, allowing them to efficiently transfer loads while minimizing material usage. Truss members are not limited to rigid beams. They can also include tensile elements, such as cables. The fundamental principle is efficient use of materials, with certain members functioning primarily in compression while others work exclusively in tension. Famous applications of trusses include well-known bridges such as the Viaduc de Millau in southern France, designed by Norman Foster in the early 2000s. The concept of truss structures has been pushed to its limits with tensegrity, a structural principle that relies on a combination of isolated compression elements, rigid struts, and continuous tension elements, cables or strings, to create a self-supporting system. Popularized by Buckminster Fuller, this innovative approach has found applications in engineering, architecture, and even contemporary art, inspiring new ways to achieve strength and stability with minimal material use. In architecture, the simplest type of truss is a triangular structure consisting of two rafters and a horizontal beam or tie beam, which functions in tension. Traditionally used in gable roofs and made of wood, trusses can feature variations in reinforcing members within the triangular framework. It is important to clarify that there are two alternative structural systems for supporting gable roofs, each with distinct load-bearing characteristics and material efficiency. The truss system, as mentioned, features rafters and tie beams that are connected at their ends, forming a rigid triangular unit. In the post and lintel system, by contrast, the cross beam is not directly connected to the rafters. Instead, the rafters rest on vertical posts, which are supported by the cross beam. This system is less material efficient than the truss, as the posts induce significant bending forces in the cross beam, requiring more substantial beams. Now, when searching for the earliest evidence of trusses, it is crucial to recognize that trusses were not the only structural solution. Many historical structures that may initially appear to be trusses are in fact more closely related to the post and lintel system. Tracing back the origins of the truss is challenging due to the fact that wood is a perishable material. While we have extensive evidence of original wooden trusses from the Middle Ages, traces become scarcer as we go further back in time. Our journey will unfold in two parts. First, the architectural evidence. We will explore ancient architectural remains to identify the earliest confirmed evidence of trusses in architecture and engineering. Second, structural concepts beyond architecture. We will extend our discussion from trusses to the broader structural concept, examining non-architectural evidence, particularly from shipbuilding, where similar principles were applied from early on. The earliest known trusses still in place belonged to the Church of Saint Catherine in the monastery on Mount Sinai in Egypt, built around 550 AD. This is the oldest consistently inhabited Christian monastery in the world. Continued maintenance in the dry climate of Egypt ensured the preservation of the original 6th century trusses at St. Catherine's Monastery. These trusses follow a relatively simple triangular system with a king post, a vertical central member, and two diagonal members bracing the rafters. All connections were crafted using mortise and tenon joints. Further back in time, documentation exists of earlier trusses dating as early as the 4th century AD in some of the earliest Christian churches in Rome. Here on the right, the old St. Peter's Basilica, constructed in the 4th century AD, before being demolished to make way for the Renaissance Basilica, was recorded in architectural drawings, later published by Carlo Fontana. On the left, top left, the Basilica of St. Paul outside the walls, also built in the 4th century BC, featured a similar roofing system with wooden trusses. Although the church was destroyed by fire in 1823, its structure had been documented in drawings and descriptions by several architects. Taking another step back in time, we arrive at the Pantheon, built under Emperor Hadrian between 118 and 126 AD. While the original trusses of the portico were replaced in 1625, they are well documented in Renaissance and Baroque architectural drawings, including those by Palladio and Borromini. Notably, these trusses were made of bronze, with an upside-down U-shaped cross-section, and were joined by large rivets, one of which is still preserved today. Going even further back, we find a remarkable early application of truss principles in bridge construction. Trajan's Bridge, completed in 105 AD, likely designed by the renowned architect Apollodorus of Damascus. This bridge spanned the Danube River, covering nearly half a mile, an extraordinary engineering feat for its time. The bridge is depicted in reliefs on Trajan's column in Rome, providing valuable visual documentation of its structure. While more complex than the triangular roof trusses we previously examined, the bridge relied on the same fundamental concept, a structural framework composed of straight members connected at their ends to form a rigid system, allowing for both strength and material efficiency. Even earlier, recent excavations have uncovered remarkable evidence of trusses at Herculaneum, near Pompeii. During the catastrophic eruption of Mount Vesuvius in 79 AD, an earthquake caused the collapse of a wooden roof, which was then buried under volcanic mud and later sealed by a layer of lava. This unique preservation allowed archaeologists in 2011 to uncover and study the components of a 7-meter wide truss remarkably intact. The reconstructed truss features a triangular framework with two smaller components forming a pseudo-king post in the middle. Not long before the events at Herculaneum, the ancient Roman architect Vitruvius provided written evidence of trussed roofs in his treatise De Architectura, the 10 books on architecture, written in the second half of the 1st century BC. In Book 5, he describes the roofs of Roman basilicas as being formed by a cross beam combined with sloping beams, a description that many scholars interpret as referring to trusses. The first basilicas appeared in Rome in the 2nd century BC, and it is widely believed that the large central naves of these buildings required trusses for structural supports. Now, this represents the earliest textual evidence of trusses in Roman architecture, and the furthest we can trace them in the Roman world before the trail of evidence runs out. We now shift our focus to Greece and the Greek colonies in southern Italy. Did the Greeks develop and use trusses before the Romans? One major challenge in tracing trusses in Greek architecture is the lack of preserved roof structures from ancient Greek buildings. And as a result, the evidence for Greek trusses can only be indirect, primarily inferred from beam sockets and other traces preserved in the stone blocks of temples and other buildings. In a seminal study published in 1960, Trevor Hodge analyzed beam sockets in Greek temples and argued that Greek temple roofs were not trussed, but instead followed a post and lintel system. In this system, rafters were not attached directly to cross beams, but were supported by purlins and vertical posts. Later studies have confirmed this interpretation, showing that this was the dominant roofing system in Greek monumental architecture. However, there were exceptions. As early as the 6th century BC, some small temples in the Greek colony of Selinunte in Sicily were likely roofed with structures akin to trusses. The clearest example is the Temple of Malophoros, which featured an interior span of approximately 8.5 meters, or about 27.5 feet. The Temple of Malophoros was built using stone ashlar masonry and featured a cornice with slots designed to accommodate the roof structure. These slots provide crucial indirect evidence, allowing scholars to infer the presence of a trussed system rather than a simple post and lintel structure, and making it one of the earliest known examples of a trussed roof in Greek architecture. To find even earlier evidence of trusses, we must look further east, to the Anatolian Peninsula, and particularly to the Kingdom of Phrygia, home to the legendary king Midas. The necropolis at Midas city in Phrygia features rock-cut tombs dating as early as the 8th century BC, including the so-called Midas tomb. These tombs often incorporate pediment-like elements in their facades. Some scholars interpret these elements as representations of trussed structures, suggesting that trusses, or at least the concept of triangular framing, may have been familiar to Phrygian builders. We now reach the end of the first part of our journey, remaining in Anatolia, but taking a considerable leap back in time to the first half of the 3rd millennium BC. The earliest known evidence suggesting the use of trusses comes from huts made of perishable materials such as mud and wattle. Excavations at Karatash in southern Anatolia uncovered a piece of mud from the top of a wall that bore the imprints of two timbers lashed together. These timbers likely formed a rafter and tie beam, suggesting the presence of a rudimentary truss system. This discovery represents the earliest physical evidence of truss construction, demonstrating that the fundamental principles of trusses may have been in use over 4,000 years ago. Having explored architectural evidence, we now turn to the second part of our investigation. Can non-architectural evidence help us trace the origins of the truss concept? One particularly intriguing connection emerges with traditional ship building. Like roofs, ships were large wooden structures subjected to considerable mechanical stresses. Additionally, there are linguistic parallels between elongated roofed spaces and ships. For example, in many languages, the central aisle of a church is called a nave, a term derived from the Latin navis, meaning ship. There are clear formal similarities between an elongated gable roof and a ship turned upside down. More importantly for our study, both structures rely on longitudinal timbers connected to crosswise frames that provide rigidity. In architecture, these crosswise frames take the form of trusses. This raises the question, do we find similar structures in shipbuilding? Indeed, one traditional method of ship construction involves pseudo-triangular frames, consisting of two symmetrical ribs and a cross-beam or thwart attached to them. However, other shipbuilding techniques do not directly connect the ribs to the thwarts in this way. Studying early ship structures is difficult because shipwrecks are typically only preserved at the bottom of the hull, which becomes buried in sand soon after sinking, protecting only the lower portions of the vessel. However, some exceptional finds in dry environments have provided rare insights into complete ship structures. One of the best preserved examples is the famous sun boat of Pharaoh Cheops in Egypt, designed for navigation on the Nile River and ritually buried next to Cheops' pyramid at Giza around the middle of the 3rd millennium BC. Interestingly, the sun boat of Cheops did not feature a pseudo-truss structure. The vessel's ribs were not connected to the thwarts, meaning there is no equivalent to a truss-like triangular framework in its construction. Instead, rigidity was achieved differently, using an ancient technique where all timbers were lashed together. Analysis of ancient shipwrecks should suggest that this method remained the dominant shipbuilding technique throughout most of antiquity, rather than rigid truss-like connections. But again, there are exceptions. At the ancient Greek site of Massalia, modern Marseille, on the Mediterranean coast of France, archaeologists uncovered the remains of a fishing vessel from the second half of the 6th century BC. The hull was sufficiently preserved to show ribs attached to a central stanchion that presumably held a thwart. The excavators reconstructed an interior structure with pseudo-triangular frames consisting of curved ribs attached to thwarts that we may call pseudo-trusses. Interestingly, this corresponds to roughly the same period, the 6th century BC, when Greek builders in Sicily were also experimenting with trussed roofs, as we previously observed. If we look for more general instances of the structural concept behind the truss, some interesting findings emerge. Returning to Egyptian vessels, we see a notable feature, the bipod mast, an elongated triangular structure consisting of two main timbers connected by tie beams. Here you see another depiction of the bipod mast, shown in a relief from the pyramid of Pharaoh Sahure, dating to the middle of the 3rd millennium BC. This depiction is particularly interesting because it shows the bipod mast being raised, but also for another reason. If you look carefully, you'll see that above the hull, there are 3 vertical posts that keep a thick rope in tension. This rope was firmly tied to the 2 ends of the hull. Now, what was its purpose? Unlike the previously shown river boats, this vessel was designed for open sea navigation and needed to be stiffer against long waves flowing perpendicularly to the hull, which could have caused it to break apart. This is a well-known problem in naval engineering, and even in modern times, many ships have wrecked due to this structural challenge. Egyptian shipwrights devised an ingenious method to stiffen the vessel longitudinally. As a whole, this structure can be interpreted as a rigid, compression-resistant element at the bottom, attached to a tension-resistant cable at the top, with posts in between keeping the cable in tension and effectively counteracting upward bending. Now, modern engineers would describe this as a hogging truss. This was not an isolated example. Many depictions, dating over a period of more than 1,000 years, show the same structural concept in Egyptian vessels. These structures clearly resemble certain types of trusses that were extensively experimented with beginning in the 19th century, and eventually led to the development of cable-stayed trusses and similar structures, influencing modern trusses, bridges, towers, and other engineering applications. And in a certain sense, from these early Egyptian experiments to tensegrity, the conceptual step is not as long as one might think. In conclusion, we first searched for the earliest evidence of trusses in ancient architecture and engineering, and we found that the earliest known trusses in Roman architecture date from the 1st century BC, but indirect evidence suggests that they were used in basilicas as early as the 2nd century BC. Next, Greek architects generally preferred the post and lintel system, but occasionally experimented with trusses, as seen at Selinunte. Possible trusses represented on Phrygian tombs suggest their use in Anatolia as early as the 8th century BC. But the earliest evidence of all comes from prehistoric huts in southern Anatolia, where findings suggest that simple truss-like structures were already in use in the 3rd millennium BC. Next, we asked whether non-architectural evidence could help trace the broader concept of the truss. We found several applications in shipbuilding. Greek vessels show occasional experiments with pseudo-trusses appearing around the same time, 6th century BC, as trussed roofs in Sicily. In Egypt, the triangular bipod mast and cabled structures of seafaring vessels reveal an advanced understanding of structural mechanics, anticipating complex cabled structures still used today. Now, modern architects and scholars sometimes underestimate the ingenuity of ancient builders, but the evidence tells a different story. Concepts we consider modern were oftentimes invented, forgotten, and rediscovered many times throughout history.